Hello and welcome to this module on adaptive signal processing, which is part of this course Electronic System for Sensor Application, and my name is Raj Babu. I will be handling this module. So this module is an on adaptive signal processing, and this session will give an outline of what we intend to cover under this topic. So if you look at the objective, the main objective of this course is to focus on advanced signal processing aspects which relate to modern electronic systems. These modern electronic systems include hearing aids, smart watches, home audio systems, and many other such applications. While the other parts of the course deal with the electronic components themselves, this module will deal about the signal processing aspects involved in these systems. With that objective, the motivation for having this module on adaptive signal processing is to move from deterministic signals and time invariant systems, which you had done in the previous courses, to non-deterministic or so-called random signals and time varying systems. So we will see what are the things involved when we want to look at handling non-deterministic signals and as well as time varying systems. The way we look at this is by covering these topics here, which are outlined here. Is we start off with design and analysis of optimal filters. We will define what optimal means when we get to that point. We move on to time varying systems, which in some case may be linear and in other case may be non-linear. Once we understand these three ideas, we will look at some applications which apply these ideas into real world applications. To understand a little better, let's just look at this. So traditionally, conventional signal processing systems can be looked at as linear time invariant system, where you have signals or signal going into a system which we have typically understood as linear time invariant systems. Time invariant systems, and the output of this system is signal of interest. So we typically say that these signals can be denoted as x of t and output signals as y of t, where if you are looking at continuous time systems, this is how we have, this is the notion of systems which we are more familiar with. And in previous courses, you would have studied and understood more about these linear time invariant systems, which have very good properties, assuming your input signals or deterministic signals. And accordingly, depending on the applications which you are interested in, you could design such systems to get such outputs, which could be, let's say, filtering some certain frequency components from a signal which has more frequency components, which typically is a filter, and this is what we are more used to. What we intend to do in this module of this course is to look at not just deterministic signals, but we move to what are called as non-deterministic signals or random signals or processes, which could be, one way of looking at them is a signal x of t corrupted by some signal, maybe a noise signal, which could be described in a probabilistic or statistical sense. So this input can be thought of as a non-deterministic or random signal. So with this input into the system may still be LTI, or it could even be a time varying system, which we will indicate as, let's say, a time varying system, and whose output again may be some desired signal but may not be accurate. So what this course intends to do is understand as to how to represent these non-deterministic signals, which directly comes from things which you have done in the past, which is random processes. Then analyzing such signals would need some understanding of the system which these signals go through, and either you can model systems or try to model such systems based on an observed signal. So essentially this is kind of the transitioning from deterministic signal to non-deterministic signals, time invariant systems to time variant systems. At times these linear time invariant systems can still be linear time varying systems, or they can even be non-linear time varying systems, and our objective is to see how to handle such systems and analyze them so that we can achieve the desired output in a real world application. So moving on, the expected prerequisites for this course include a course on digital signal processing, which I'm assuming most of you would have done, where you would have seen properties like how to sample continuous time signals to get discrete and digital signals. Moving on from sampling, we would have looked at LTI systems or linear time invariant systems, analyzing such linear time invariant systems, understanding the properties of these linear time invariant systems such as frequency response, magnitude response, and also implementing such systems. For example, implementing an finite impulse response filter, which is an FIR filter or an IIR filter, or designing such filters. Okay. So these are things which is expected as prerequisite as part of the digital signal processing course, and most of you again would have taken a prior or a basic course on probability, random processes, and statistical analysis. While we would not review too much of the digital signal processing part, we will do a review of some concepts which are more often used in this module when we look at adaptive signal processing or adaptive systems. So as we go along, we will understand better how these random processes play a key role in analyzing and understanding adaptive systems. With that prerequisites, what we intend to cover in this course is outlined here. So we will start off with the review on random processes, which essentially starts from random variables, moves to random processes, defining them, understanding properties such as stationarity or white sense stationarity of random processes, and then how that relates to power spectrum, what are correlation, covariance. These are the concepts which we will be reviewing in this random process lecture on random process. With that short review and introduction, we will move on to look at what are called as optimal filters. So these optimal filters differ from the traditional FIR and IIR filters, where the objective may not have necessarily been to achieve an optimal filter. The objective would have been to realize some expected frequency response. So if you kind of extend that, and if you want to do this using an optimal filter in some sense, and that's what we are going to do, so that this forms the framework for what adaptive systems will be using and how they will be designed. As part of looking at these optimal filters, we will look at the well-known Wiener filter. The filters here essentially refers to different variants of the Wiener filter, where it could be a finite length or an infinite length filter, and so these are some of the things which we will cover under this topic on optimal filters. Once we know what is optimal in terms of performance, we will try to move from optimum filters which usually, or let's say, under non-realistic assumptions. So we will relax these non-realistic assumptions and go to real world signals whose statistics may change with time. For example, we will move away from white sense stationary signals to non-white sense stationary signals and see how to handle such signals. So that will take us to one of the well-known forms of adaptive filters, which is called as this LMS filter, or the least mean square filter. Another variant of this adaptive filter, which may or may not be looked at as an adaptive filter, is a recursive least square filter, which again is a implementation which helps us to achieve real world applications in a more computationally efficient way. And they have performances better than the LMS filter in certain cases, and we will look at when such filters are more useful. Having looked at these adaptive filters and recursive least filters, we will look at two or more specific kinds of filters which are very well known and popular in adaptive signal processing topics. Though they may not fit directly into the adaptive signal processing topic, they are very relevant and close to the topics which we are covering in the course. That includes Kalman filter, which is optimal in some sense, but if you relax certain assumptions, they may not be the optimal filter. And then we move on to look at neural networks, which is one basic but important application of adaptive filters. And nowadays they have become much more prevalent and popular because of this deep neural networks. This course will not cover deep neural networks, but this will give you the basic ideas of on what the neural networks works and how it relates to some of the adaptive filtering concepts which we discuss in this course. With this kind of theoretical background on these topics, of course there will be examples on these topics as we go along. Towards the end, we will look at specific applications of these topics with problems which are well known in each of their own field. For example, linear prediction in speech processing, adaptive noise cancellation, which is very popular and used in hearing aids applications. While system identification may not be focused a lot, but we will give insights on what system identification means and how it relates to the topics which we cover in this course. And same with inverse modeling, where given any signal, if you are interested in getting the system, how do we do it? So while some of these are or can be applied in a deterministic setting, we will look at them in a way more suitable for this adaptive signal processing systems and signals, and we will try to interpret them as we go along. So before kind of summarizing this outline, I will try to show one simple application which you can either think of as a motivation as to why we need to look at adaptive signal processing or systems which handle random processes. So what is shown here is at the top we have a white noise signal, which is one kind of random process, which can be thought of as having a flat power spectrum, which means it has frequency components across all frequencies in a similar strength. Assume that it is given as an input to a linear time invariant system, which is, let's say, an IIR system, if you are familiar with, which you are familiar with. This system has two poles and correspondingly two zeros. So this can be called as what is typically known as an autoregressive model, because it has only poles. So what we intend to do in this course is, if let's say this system is unknown, that there was a second order or a IIR filter involved in some processing, and you are only given, let us say, this output signals, which could be this filtered signal at the third plot. The objective is, given this signal, can we, and if you are said that this is one of the signal which models well known process, for example speech, can we come up with the system which generated this signal, right? So this is kind of one of the applications which you could think of as to design an adaptive filter. So in this case, we may start with an initial assumption, and if you know the model structure, you assume that it has two poles. You start with certain coefficients and try to see at what coefficient does the output of this model matches this model closely. So what is given at the bottom is a stage in that processing. So we have defined certain parameter values for the poles. Based on that, you have an output when the input is white noise signal. So you can see that these two signals are not exactly same. That's because these parameters are not matching yet. So the objective in adaptive signal processing or the adaptive systems is to try to get to the coefficients of this system which will generate an output like this if the input is a white noise signal. So how do we do this continuously even if this signal keeps changing? So for example, in this case, the signal keeps changing, but the statistics is kind of remains same throughout. But there can be signals where the statistics changes over time and the system may not change, but despite the change in the statistics of the signal, can we design or adapt or find a system which will help us get to this desired signal, right? So that in some sense is the objective of this course, and the reason why we have a estimation or a spectral estimation here is, another way of looking at it is, rather than just trying to get this signal, you could also look at it, if it is a, let us say a random process, you could define its autocorrelation and then accordingly its power spectrum, and our objective is to estimate this power spectrum. While we will not focus too much on the power spectrum itself, what we will focus on is in the getting to this adaptive system, but it is always good to have this notion that how adaptive signal processing or trying to design adaptive filters can also help us in doing spectral estimation or the vice versa. So with that brief introduction to what this course would be and the outline of this course, I would like to point out these references. The first reference is a book by Professor Monson Hayes, which is on statistical signal processing and modeling. This is a recommended book which covers a wide variety of topics, including the adaptive signal processing and appropriate prerequisite topics also. And then the second one is probably a little difficult to get hold of, is this book by Professor Therian, which is Discrete Random Signals and Statistical Signal Processing. This has good insights into random processes and how systems behave when the inputs to the systems or random process. So with that, so we come to the end of the first lecture in this module on adaptive signal processing. For the next lecture, I would recommend that you get prepared on random processes, where we will review some aspects of random process and look at how they will be applicable to this course on adaptive signal processing. Thanks for listening and see you in the next lecture.